Why do some particles, seemingly stable, suddenly change their flavor or identity? Imagine a particle like a neutron, which, after a while, transforms into a proton and even ejects an electron. The textbooks typically gloss over this and explain it as a result of the weak interaction, where quarks exchange W and Z bosons, triggering a flavor change from a D quark to a U quark, turning a neutron into a proton. This might seem straightforward, but when you examine it more closely, two crucial things are missing from this explanation. First, what exactly happens when the W and Z bosons are exchanged? Why does a neutron have to undergo such a drastic transformation to become a proton? Why can't it just shake up a little and remain a neutron? Secondly, while we see particles changing flavors and identities, textbooks still talk about it as if it's just another force pulling particles around, as if the weak interaction is merely a weak force acting over a short distance, instead of explaining the underlying process in a more nuanced way. In the energy filament theory, weak interaction behaves very differently from the strong force or electromagnetism. The strong force essentially deals with gap filling. When there's a gap such as between quarks, the gluon wave packets, mediators of the strong force, rushing in to fill it, stabilizing the system. This is an automatic process when the gap grows too large. Electromagnetic force, on the other hand, is concerned with the orientation of energy fields, determining how charged particles attract or repel each other. The weak interaction, however, governs a completely different phenomenon. It operates on the textures of the internal particle structure itself. When particles are unstable, their internal configuration becomes misaligned, and weak interaction steps in to restore balance by reconfiguring the internal structure of the particles, not by applying external forces. You can think of unstable particles as tangled knots. These knots may stay together for a while, but their internal structure is constantly under tension, as if something is pushing them to untangle. The weak interaction's role is not to add more force, but to create a tiny reconnection gate at an incredibly small scale. This gate allows certain strands of the particle's internal structure to subtly detach from their original connections and rejoin at a more stable location. In simpler terms, this is the mechanism behind a particle's flavor change, where quarks undergo a shift in identity. The weak interaction allows this reorganization to happen in the most energy-efficient way, leading to the transformation from one particle type to another, such as from neutron to proton. This transformation is observed as beta decay. So, why does weak interaction govern this process instead of the strong forces? The reason is simple. The issue isn't about filling a gap or applying an external force. The weak interaction addresses internal instability. It works by reconfiguring the structure to allow for greater stability, which is why it's responsible for particle decay. The strong force, which is about stabilizing the system by filling gaps, isn't equipped to handle this kind of structural realignment. Moreover, because weak interaction deals with structural instability, it's directly tied to particle lifespans and half-lives. If a particle's internal configuration is unstable, it will eventually decay via weak interactions. This explains why particles with unstable internal configurations decay faster than more stable ones. It's all about how efficiently the particles can rearrange itself into a more stable configuration. Next time, we'll dive deeper into the question, why must unstable particles decay? Stay tuned, hit follow, and share this. We're exploring new physics in this series, helping you better understand the universe.